Okay, so this lesson is about classes of functions and transformations. This will not be something new. It might be presented in a slightly different way, okay? So that's the main difference. It might be presented in a slightly different way. So let's go over our rules of transformations. If we have some function we'll call f of x, and we want to move that function to the left, remember to do that, we are going to add that thing on the inside of our function. Actually, let me call that h. So if we add on the inside of function, it's going to move it left. If we subtract on the inside of the function, it's going to move it to the right. To move a function up, remember we're going to add on the outside of the function. To move a function down, we're going to subtract on the outside of the function. If we want to flip our function down across the x-axis, we are going to multiply on the outside. Now think about anything that changes vertically, up and down, will happen on the outside of the function. Any changes from left to right, so horizontally, will happen on the inside of the function. So that's the way to remember these two. So here, our change is on the inside of the function, okay? Stretching and condensing. So let's kind of talk about what that means. Okay, so if we want to stretch it vertically, then our a has to be bigger than 1, and it is going to be on the outside of our function, okay? If we want to condense it vertically, and let's even say the absolute value of a has to be greater than 1. Let me make that prettier. The reason I put the absolute value is because it might be a negative. The negative does one thing, it flips it. The value does something else. If the absolute value of a is less than 1, so think of a proper fraction: 1/2, 1/3, 2/3, 2/4, 2/4. Anyway, then if it's on the outside, it will condense it closer to the x-axis. Remember, anything on the outside changes it vertically, so it's going to squish it closer to the x-axis if a is a proper fraction. If a is more than 1, so an improper fraction, or a whole number bigger than 1, it is going to stretch it further away vertically from the x-axis. Now let's talk about horizontal. Now remember, horizontal happens on the inside of the function. Remember, it happens on the inside of the function. What's weird though, it always kind of does the opposite of what you want it to do. It has just that kind of an opposite effect. So here, if our a is less than 1, so a proper fraction, and it's on the inside, it will stretch it left to right. It will pull it outward. If our a is greater than 1 and it's on the inside, then it is going to condense it left to right. It is going to squish it in. So if you think about a perfect example for stretching and condensing horizontally is our sine and cosine function. You might recall if you had something on the x, it might change that period of our function. It might change how fast it is. So if we think about Slinky, if we had a number that was a fraction in there. So if we had like x over 2 inside of our sine or cosine function, it is going to stretch it out. But if we had 2x inside of our function, it will smush that spring in. Okay. Any rules about or any questions about our transformation rules? Okay, so those you should know. We went over all those last year, but we didn't necessarily just kept calling it F. You'll see that it won't necessarily always give you the actual function. Okay, now let's talk about rules of symmetry. For an even function, when we stick a negative inside, let's go even here. If we stick a negative inside our function, it is the same as the original. It has y-axis symmetry. It has y-axis symmetry. Okay. If it is odd, when we stick the negative inside of our function, it is the opposite. So it has origin symmetry. Some other ways to think about it. The point xy is on your graph. Here, the point negative xy will also be on the graph. Here, if the point xy is on your graph, then the point negative x, negative y is also on your graph. So for an even function, just look on each side of your y-axis. You can fold it over. It's a perfect match. Now, an odd one's different. I think of it as a kind of flip-flip situation. If it's in the first quadrant, if you flip it across the y and then flip it across the x, it'll land in the third quadrant. So kind of a flip-flip sort of situation will be an odd function. And you should be able, it will go through the origin, and you should be able to spin it at the origin, and it should look like a pinwheel. It will look right back the way it started. Okay. Lots of review in this section because we did so much last year with functions. Hopefully you know about functions, we hope. Okay, x-intercept. You're going to let y equal 0, and then you solve for x. It is of the form a0. A function may have multiple x-intercepts, but it can only ever have at most one y-intercept. Remember, a function passes the vertical line test, so if it had more than one y-intercept, it would fail that test. For the y-intercept, you're going to let x equal 0, and then you solve for y. And it is of the form 0b. So again, for a function, it might have multiple x-intercepts, but it can only ever have one y-intercept. The y-intercept's the easier one. You just plug in 0, get a number, bam, you're done. The x-intercept, because it's the y, or remember, that's really our f of x. Since it's the y or the f of x, you may have to factor, use the quadratic formula, do stuff. It's usually not quite as cut and dry and beautiful to find an x-intercept than it is to find a y-intercept. Everybody good there? Okay. Let's talk about our parent functions. You have to know the parent functions. Last year we did our parent functions together. That is something we remember. I think we even had a parent function quiz. If you have any of those notes from last year, it might be a good idea to go and look at some of those parent functions. But let's just go over what they are, and then I'll draw just a general diagram of what the heck they look like, okay? So our linear parent function is y equals x. It goes through the points -1, -1, 0, 0, 1, 1. I can never draw a line. I'm sorry. I think you get the drift. Okay, So anyway, that is your linear parent function. Just is a line with slope of 1 that goes through the origin. Quadratic, y equals x squared. Remember, that's just our parabola. It goes through 0, 0, 1, 1, and negative 1, 1. You can even go 2, 4, negative 2, 4, 3, 9, and negative 3, 9. So that shouldn't be anything that you question in your brain. That should just be something, hopefully, that happens. Next is our cubic. Our cubic function, y equals x cubed. Remember that one has origin symmetry. So 0, 0, 1, 1, 2 goes all the way up to 8. And then any points that repeat themselves in the first quadrant, the negative version appears in the third. So negative 1, negative 1, negative 2, negative 8. So it looks something like that. So that is your cubic function. The square root function you can write as the square root of x or x to the 1/2. They mean exactly the same thing. Remember, they go through the points 0, 0, 1, 1, 4, 2. The cube root function, you'll see that little index of 3, but remember, you can also write that as a 1/3. It not only has the swoop to the right, 0, 0, 1, 1, 8, it becomes 2. So it's steeper like the cubic function, but it has a piece over here. So it has a piece on both sides of your, has a piece on both sides. Okay. My graph paper is getting beautiful. Yeah, anyway. Next one, absolute value is y equals the absolute value with absolute value bars. It's a good thing based upon what we're going to be doing with an absolute value later on, that you remember that that's a v. Its piecewise function looks like this. It is the opposite of x for x less than 0. It is the same if x is greater than or equal to 0. So the first piece is a line with slope of -1, and then when you get to 0, you switch to a line of slope of 1. So it will cover up part of my line here. So it actually is the same as the identity function in that first quadrant. So that's a perfect little V that splits the first and second quadrant. Next is our reciprocal function. That's y equals 1 over x, or y equals x to the -1. Remember, a negative exponent tells me it's going to be a reciprocal. Now, if it is a -1 or an odd power, it is going to have 2 pieces. It's going to stay an odd function. If it is an even power, that does have a little bit of a flip thing that happens to it. But that one has it technically has a dashed line on the x and y axis. It never touches any of those things. It goes through 1, 1, negative 1, negative 1. It is an odd function. It's got that little piece that's getting closer to each of those. I apologize for the ugliness, but so that is what your reciprocal function looks like. The y equals x, 1 over x squared, both pieces are up here. So if it's an even negative power, it will be 2 pieces in the top or bottom, depending. And then for an odd function, for if that's an odd number, they'll be in opposite locations. Okay. Trig, yeah. So the way that I normally do it is I go to, just go to Google and search for graph paper. And I don't really find actually paper. I just pull up a sheet of paper and I do a screenshot of it and put it into my photos. And then I insert a photo. So I try to always have graph paper just in my photos, so then if I need it, I can put it in there. Does that make sense? Now, let's talk about our trig functions, okay? For trig, let's think about our sine graph, okay? This time I needed the trig graph paper. The main thing to remember about our sine graph is that it starts at 0, always has a height of 1 or negative 1. It comes back down at pi. At pi over 2, that's a horrible placement of that. Bing, 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 bing. Let's make that pi. 1, 2, 3, 4. It hits a height of 1 at pi over 2, and then goes back down. And remember, it just keeps repeating that process from left to right. Sorry, that's so gross, but our cosine function starts at 1. Its bump hits 0 at pi over 2. At pi, it's at negative 1. So that's your cosine function right there. It's really the sine function shifted over a little bit. So every place that the sine is 0, the cosine is either 1 or negative 1, if that helps. But just if you remember that the sine starts at 0 and goes up, but the cosine starts at 1 and comes down. That's the main thing to remember, the difference, okay? So let me say it again. The sine starts at 0 and goes up. The cosine starts at 1 and comes down. These are, that's 1 and negative 1. This is pi over 2 pi, 3 pi over 2, and 2 pi. Remember those 0, pi over 2 pi, 3 pi over 2, and 2 pi. That's the most easy way. Those 5 points is what we really kind of focused on when we were graphing sines and cosines. Don't worry about the tangent graph. It's not going to come up very often. If it does, I'll remind you of it. Usually in trig, knowing the sine and the cosine are going to be the most important ones to remember. And then lastly, log and exponential. So let's talk about log and exponential functions. For a logarithm, let me put my x and y axis. Okay, for a logarithm, we can't plug negative numbers into a logarithm. So there's a little border right here. So it will never go into negative territory. Wait, that's an exponential. Wait, stop. Okay, let's say that again. Let's start with exponential. So let's go 2 to the x, just for the heck of it. Okay. So really any exponential will have a horizontal asymptote at 0. It can never cross down into the negative category. And so it always has something real, a tail on the left, really super close to 0. It's going to hit the point 0, 1. And then depending on its base, it will shoot up like that. Okay, so that's the exponential. Now, think about the log is the inverse of it. So if we flip it across the line, y equals x. So if we flipped it across that line, let's think about what that does. So let's say we have y equals the log base 2 of x. So now we want to do the inverse. The inverse will have a vertical asymptote at 0. We can't plug x's in that are negative into a logarithm. It messes it up. There's nothing we could put on a 2 to turn it into a negative number. So it's the same graph kind of laid on its side. So now it has a tail that goes down here, hits the point 1, 0, and then shoots out. So you can see that it's like folded across this line. So this one is the exponential, and that one is the log. One has a horizontal asymptote at 0, the other has a vertical asymptote at 0. So that's just a very, very quick rundown of what the graphs are going to look like. It is your responsibility to know and remember, hopefully, how to graph them. Let's talk about the assignment that's given. We'll do one of them, and you'll notice that there are 15 of them, and it asks a lot of you, okay? It asks if it's even or odd, decreasing, increasing, and behavior, domain, and range. So let's do one of them, and let's identify the type of graphs, okay? First, let's identify the graphs. Problems 1 through 4 should look like it's just a parabola, okay? Now, it has been altered using the rules of transformations. You shouldn't have a hard time graphing them. I need at least 3-point accuracy. If you can give me a little bit more than that, that's great. So let's do number 1 together. So it says sketch the graph using transformations. So this tells us that we have moved to the left 4, and this says we have gone down 1. So all we have to do is take the original points of a parabola, negative 1, 1, 0, 0, and 1, 1, scooch them down 4, left 4, down 1. Okay, so you might want to put on the original so that you can graph the new one. Do you have to put the original? Not at all. Is it helpful? Yes, because what can we do? Well, we can take the original point. We can jump 1, 2, 3, 4, down 1, 2. And we know that that origin is going to go right here. And then do it for every other point. And then make that one the solid one. So 3 points accuracy. I prefer if you can give me 4 or 5, that's great. Now we're ready for answering the questions. So the intercepts. If you set this equal to 0, you're going to find the x-intercepts. Remember, where the function equals 0 is the x-intercepts. The y-intercept, so that's, I'm sorry, that writing was very sloppy. So that's -4 plus or minus 1. So that's going to be what? -3 or -5. And if I would have drawn it somewhat accurately, I should have gone a little bit steeper. But anyway, your y-intercept, if you just let it be equal to 0, that's going to be 16 minus 1 or 15. Okay, and that's why it's off the chart. So if it's off the chart, so be it. Okay. Next, let's talk about, is it even or odd? Most of these are not going to have much symmetry, because if you move them away from the y-axis, you've messed up y-axis symmetry. If you've moved it away from the origin, you've messed up origin symmetry. So there's no symmetry. It's not even or odd or anything exciting. Decreasing and increasing intervals. Let's see what you remember. This function is decreasing. Remember my little math bug? He's going downhill, and then he's going uphill. And what value does it switch over? What x value? -4, right? So it is increasing for an x value of -infinity to -4, and then that's decreasing. Gosh. And then it is increasing for an x value of -4 to infinity. Now, let me remind you about that. It is very important that you remember about increasing or decreasing, because of some things that are coming on later down next, probably next semester. But anyway, this function, this means, okay, let's go over it again. This is what the y is doing along this x path. So from an x value of -infinity to an x value of -4, my function is decreasing. And then from an x value of -4 to an x value of forever and ever and ever, my function is increasing. So remember, the word is describing what the y is doing. The x, that's why I always put x equals on the interval to remind me that's what the x is doing. Okay. And then end behavior. For now, just say left. What's our left doing? Our left is going to positive infinity. Our right is going to positive infinity. We will eventually use the correct calculus notation for that. We're going to use a limit notation for those. Right now, it's not that necessary, okay? Last thing you got to tell me. Yes, there's a lot for each problem. That's why these aren't due until Friday, I think. I think. Does not want to cooperate, does it? The last thing is domain and range. Remember, domain are what x values I can plug in. How does my graph stretch from left to right? See how this graph is going from -infinity to positive infinity. There's no x's that you can't plug into a parabola. But the range does have a low point or a high point, depending on if your parabola is an upward facing one or a downward facing one. What is the lowest point of this graph? -4. What is the highest point of this graph? Infinity. So the range is low to high. Oh, I'm sorry. It should be negative. Oh, that's why. Goodness gracious. Okay. Yeah. Let's see. Let's go back. That's why my intercepts looked so funky. I'm doing good today. No, just the graph. Okay. Over 4, down 1. Makes me hit those points exactly. Yeah. Sorry. Like, why aren't I hitting those points right? That is what my graph should be. I apologize. Yeah. Okay. Yeah, I'm doing great. Okay, so that is 1 through 4. You're just going to use your rules of parabolas. Let's do number 6 real quickly. Let's do 6. You're just going to work on these tomorrow in class. So let's take a look at number 6. What is the parent function for this one? What's it look like? What's it kind of, is it? Absolute value, right? It's your perfect little V. Here's the problem with this one. It has gone left 3, down 1. That is not down 1. My gosh. Oh, let's go back. This video needs some major edits, doesn't it? Anyway, this is going to go left 3 and up 1. This is going to flip it and stretch it away from the x-axis. So we have some things to think about. When I have something that has a number on the outside that really has an issue, I know the symmetry of a V or an upside down V. So what we're going to do to kind of make sure that we don't lose track of everything, we said that the V is going to go from 0, 0. It's going to go left 3 and up 1. So I know that -3, 1 is the vertex pointy point of my absolute value. So let's just plug in to the left of that and to the right of that just to make sure where do we head. And then I will explain something here in a minute. If you plug in -4, you get the absolute value of -1, which is 1 times -2 is -2, plus 1 is -1. Now, because of the symmetry, if we get it right, -2 should do the exact same thing. I should get that -1 again. Well, -2 plus 3 is 1. The absolute value, that's 1 times -2 is -2 plus 1 is -1. So yay, I picked the correct shifty location-y point, okay? So let's graph it. Over at -3, I am at 1. At -2 and at -4, I am at -1. Okay. So that is what my graph looks like. Now, what's so kind of interesting is when it flips over, this number here becomes the slope. Instead of a slope of 1, you'll see here this side gets a slope of 2, and this side gets a slope of -2. So if that helps you with that, but and then we're able to answer all those questions. You know, it is increasing till an x value of -3, and then it is decreasing, and so on and so on. 8, 9, and 10 and 11. Those are our square root functions. Let's do number 8. For a square root function, just look at where does x plus 4 equal 0? Where does x plus 4 equal 1? Where does x plus 4 equal 4? Square roots, perfect square roots. But we know this should move it to the left 4 units. And why does it move it to the left 4 units? Well, as soon as we subtract 4, we can see the starting location. So for this function, I would plug in -4, -3, and 0. Square roots, I always set the inside equal to 0, 1, and 4. If it was a cube root, I would set the inside equal to 0, 1, and 8. Just perfect cubes or perfect squares. If you plug in -4, you get the 0. The square root of that 0 times -2 is 0. If I plug in -3, I get 1. The square root of that's 1 times -2 is -2. You should expect that that's going to flip it over the x-axis after it's moved left 4, and then it's kind of stretched out a little bit. If I plug in 0, I get the square root of 4 is 2 times -2 is -4. So at -3, I'm at -2. At 0, I'm at -4. And then I should be able to answer my questions about that. Let's see if we can do one more example here. There's square roots. And then let's do a cube root. Let's do number 13. So for a cube root, I would set the inside equal to 0, 1, and 8, because those are perfect cubes. But you'll notice there's nothing changed on the inside. So just plug in 0, 1, and 8. The cube root of 0 is 0 plus 2 is 2. This should move my graph up 2. 1, the cube root of that is 1 plus 2 is 3. And the cube root of 8 is 2 plus 2 is 4. So at 0, I'm at 2. At 1, I'm at 3. And at 8, I'm at 4. Now, here's the thing about a cube root. Don't forget, you can plug in negatives. So let's plug in -1 and -8 as well. -1 is going to give me -1 plus 2 is 1. And then -8, the cube root of that is -2 plus 2 is 0. So my graph looks like this. The cube root has 2 pieces, a positive and a negative piece. Okay, and then you should be able to answer all the questions about your cube roots. Okay, so that is your, there is some exponentials and logs. Oh, and sines and cosines. Tomorrow we will do some of the, we'll do an exponential, we'll do a log, and we'll do some of the other graphs. We'll continue this tomorrow.